Welcome to EE5508 Semiconductor Fundamentals. My name is Professor Teo Kee Leong. This is the second half of the course. Let us first review the content. In Lecture 1, I will give an introduction, essentially an overview of semiconductors' properties. Lecture 2, we will cover the following topics on the optical processes in semiconductors. First, we will give an introduction. Then, we'll discuss the absorption, reflection, and transmission coefficient. For the absorption, we'll discuss the process whereby electron absorbed photon energy and make a transition from the valence band to the conduction band in direct bandgap semiconductors such as gallium arsenide. This is known as the direct transition. Then we'll do a quick review of phonon scattering, which has been covered in the first part of the course by Prof. Wee Hong. Next, indirect transition between indirect valleys. We'll discuss the transition of electron from the valence band to the conduction band in indirect bandgap semiconductors such as silicon and germanium. Next, we'll discuss the absorption by carrier bound to shallow donors and acceptors. Basically, electron at the donor level absorb photon energy and makes a transition to the conduction band, or electron making a transition from the valence band to the acceptor level. Session 2.4 will discuss the high doping effects in semiconductors. Some of the important phenomena are Mott transition, band tailing effect, Bernstein mode shift, and band gap narrowing. Next, we will discuss the radiative transition. Basically, we will discuss the optical process that involve emission of light, or also known as luminescence process, from the semiconductors. In the typical luminescence process, electrons in the semiconductor samples are excited electrically or optically. After some energy loss or relaxation, the excited electron returns to the ground state by emissions of light. In order for a sample to emit light, it has to be energized by some external means. We'll discuss electroluminescence, whereby the sample is excited by injection of electrons and holes through an external current, or photoluminescence. For example, electron in the valence band absorb an incoming photon energy greater than the band gap and make a transition to the conduction band, and then later recombine with the holes in the valence band and emit photon energy approximately equals to the band gap values. Other processes include thermoluminescence, emission of light by heating the semiconductor sample. Last but not least, catoluminescence, whereby the process of inducing light emission by electron bombardment. In session 2.6, we will discuss some of the important optical transition in semiconductors. For example, band-to-band transition, where electron in the valence band make a transition to the conduction band. We will also discuss how the band gap changes with temperature. Free to bound transition, basically electron which is free in the conduction band make a transition to the hole bound at the acceptor level, or electron bound at the donor level make a transition and recombine with the hole in the valence band. Donor-acceptor pair transition, electron at the donor level make a transition to the hole at the acceptor level. Optical band trap transition essentially is a capture of the electron or hole by a trap with the emission of light. Sometimes it's known as optical capture or radiative capture. Session 2.7 will discuss the concept of exciton, whereby a free electron in the conduction band and the free hole in the valence band as a pair of opposite charges experience a Coulomb attraction. Hence, the electron can orbit about the hole as this were like a hydrogen-like atom. These are known as free exciton. There are two types of exciton, and we will discuss the Wiener-Mott exciton and the Freckle exciton. We will solve the Schrödinger equation of two particles, in this case electron and hole, and derive the exciton binding energy. Besides free exciton, there are also other types of exciton known as the bound exciton. Impurity can attract exciton that become localized at the defect site, becoming a bound excitons. For example, a free hole can combine with a neutral donor to form a positively charged exciton ions. We will discuss the absorption both for the free and the bound exciton in semiconductors, and we also discuss the exciton recombination. In Lecture 3, we will cover bandgap engineering, heterojunction, and quantum wells. First, we will discuss what is semiconductor alloy. By alloying semiconductors, it affects the energy band structure, bandgap, lattice parameters, mechanical constants such as elastic moduli, and also affects the optical and electronic properties, and many other aspects of the resulting material such as scattering rate. We will talk about lattice matching of the lattice constant of the film and the substrate. We will focus more on the 3-5 semiconductors. There is group 3 element such as aluminum, gallium, indium, and group 5 element such as nitrogen, phosphorus, arsenic, and antimonite from the periodic table that form the 3-5 semiconductor. The model used in some cases for alloy is based on an interpolation scheme, such as Vergat's law and virtual crystal approximation, and they interpolate from the related binaries semiconductor. For example, aluminum gallium arsenide alloy would derive its properties from its binary semiconductors, aluminum arsenide and gallium arsenide. We will discuss how to interpolate the lattice constant bandgap energy effective mass of the alloy from the binary semiconductors. Last but not least, we will discuss spinodal decomposition. It's a process by which an alloy can separate into distinct phases, or is also called the formation of coexisting phases. In session 3.2, we will discuss heterojunction, whereby two different semiconductors are brought into contact by growing one semiconductor on top of another semiconductor. The interface or junction that is formed is known as heterojunction. We will give a quick overview of what is low-dimensional structures in semiconductors. Three-dimensional structures are bulk semiconductors. Quantum well, quantum wire, quantum dots are known as low-dimensional structures. Depending on the system dimension, one can distinguish different cases, 3D, 2D, 1D, or 0D, by comparing with the electron de Broglie wavelength. In this course, we will focus more on the two-dimensional case, which is the quantum well. The derivation of eigenfunction or the wave function and the eigenvalues or the energy values by solving Schrödinger equation has been extensively discussed in the first part by Prof. Wu Yihong. In this aspect, I will only make use of the result to discuss the optical properties in quantum well semiconductors. And we will talk about the electronic state for the infinite potential barrier and the electronic state for the finite potential barrier and the density of state in quantum well. Now, exciton occurs in 3D or bulk semiconductor, and it also occurs in two-dimensional case, which is quantum well. We will discuss the effect of exciton in quantum well as compared to exciton in bulk semiconductor. We will also discuss the optical absorption in two-dimensional case, which is quantum well. Next, we will talk about the advantages of having multiple quantum well. Session 3.8 will discuss the inter-subband transition. In this case, electron make a transition from one quantized state to another quantized state within the conduction band of the quantum well. And how does it apply to the quantum well infrared photodetectors? And how do we integrate the quantum well infrared detector with light emitting diode? Session 3.9 will discuss the application of electric field in three-dimensional case, which is bulk semiconductors, that leads to the Frank-Hardish effect, and also the application of electric field in two-dimensional case, which is quantum well, that lead to quantum confined star effect. The last session will discuss the overview of semiconductor LED in terms of its application, characteristics, and structure. And we will also talk about the carrier distribution in PN junction. How does it affect the efficiency of LED? For this second part of the course, my approach is to emphasize more on the experimental results and concepts rather than providing the details of the theory. Basically, we were based on the experimental result and provide a physical explanation rather than giving a rigorous theoretical derivation. There are many excellent reference textbooks that you can refer to. Down here, I only quoted two of them. The Fundamental of Semiconductors, Physics, Materials and Property, and the other one is the Fundamental of Solid State Engineering. Lecture 1, Introduction. Semiconductors are useful to us because of its unique electrical and optical properties that we can control. Silicon are excellent materials for electronic application, but it falls short in light emission because it is an indirect bandgap semiconductor. And it is also not suitable for high temperature and high power application. Which material are semiconductors? By looking at the periodic table, we can identify materials that form semiconductors. A single element such as silicon or germanium is sometimes called elemental semiconductors. Semiconductors that compose of two or more elements is called a compound semiconductors. So for example, in the group 3 element, you have aluminum, gallium, and indium. You have group 5, you have nitrogen, phosphorus, arsenic, and antimonite. You can form 3,5 semiconductors: aluminum nitride, aluminum phosphide, aluminum arsenide, aluminum antimonite, gallium nitride, gallium phosphide, gallium arsenide, gallium antimonite, indium nitride, indium phosphide, indium arsenide, indium antimonite. These are 3,5 semiconductors. There are also 2,6 semiconductors, group 2 element, zinc, cadmium, mercury, or beryllium, magnesium, calcium, strontium, barium, and rhodium. Group 6 will be the oxygen, sulfur, selenium, tellurium. So you can form, for example, zinc oxide, zinc sulfide, zinc selenide, or zinc telluride, cadmium oxide, cadmium sulfide, cadmium selenide, cadmium telluride, or you can form beryllium oxide, beryllium sulfide, okay, or magnesium selenide, or magnesium telluride. These are known as 2,6 semiconductors. You can also have 4,6 semiconductors, group 4 element, and then group 6 element. So, for example, lead selenide and lead telluride are 4,6 semiconductors. There are some exotic material. You can even form group 1 and 7. For example, copper and chloride, group 7 element. Copper chloride is also a semiconductor. So compound semiconductors can be 3, 5, 2, 6, 4, 6, or 1, 7 from the periodic table. Semiconductor alloy, okay, can be binary, ternary, or quaternary alloy. So alloying semiconductors can form ternary alloy and quaternary alloy. Ternary alloy, okay, usually basically are 3 elements from the periodic table. Aluminum, gallium are from group 3, and arsenic are group 5 from the periodic table. So these are ternary alloy, 3 elements. Quaternary alloy, 4 elements. Indium, gallium, group 3, arsenic phosphide, group 5. So they form the indium, gallium, arsenide, phosphide alloy semiconductors. You can even have binary alloy, for example, silicon germanium. So in principle, 35264617 ternary and quaternary are known as compound semiconductor. For alloy semiconductor, sometimes we just call it semiconductor alloy or simply compound semiconductor alloy. They could even have 5 elements and from the periodic table, and they are known as quaternary semiconductor alloy. In the first part of the course, Professor Wee Hong have discussed the physical property, that is the crystal structure, and also the electronic property, the energy band structure, and the related carrier type and the transport property. Here, we will focus more on the optical properties of semiconductors. This is the physical property of semiconductors, which I took it from Prof. Wee Hong lecture notes 3. Now, let us have a quick review of some of the important semiconductors for the application for electronics, light source, and detectors. So, important semiconductor for electronic, which is well known, is the silicon. That is the most important semiconductor system used in metal oxide, field effect transistor, bipolar devices, okay, based on silicon that form the 90% of the electronic market. Some of the disadvantage of the silicon is basically it's not as fast as some other semiconductors such as gallium arsenide, not good for high power and high temperature operation as compared to gallium nitride, cannot emit light efficiently since it's an indirect bandgap semiconductors. Silicon germanium alloy, basically silicon germanium on insulator, is a technology that is analogous to silicon on insulator technology, currently employed in computer chips. So silicon germanium on insulator increases the speed of the transistor inside the microchip by straining the crystal lattice under the metal oxide transistor gate, and it improves the electron mobility and higher driver current. The disadvantage is you need to take great care in the crystal growth condition in order to form a strain system. Gallium arsenide or gallium arsenide combined with aluminum gallium arsenide is good for your high-speed devices for digital and microwave application. For example, high electron mobility transistor, and its performance is superior to silicon. Of course, it's more expensive than silicon technology. Indium phosphide or indium gallium arsenide grow on indium phosphide. It's good for high-speed performance, superior to gallium arsenide based technology, and it can be used for long-haul optoelectronic communication technology. And the material is more expensive compared to gallium arsenide and aluminum gallium arsenide. Gallium nitride, aluminum gallium nitride are wide bandgap materials. Wide bandgap means you have a large bandgap. So gallium nitride have about 3.4 EV. And they are technologically important for high temperature and high power application. Because in the wide bandgap semiconductors, they have a higher phonon energy. And the higher phonon energy will result in the fewer optical phonon at a high operating temperature, for example greater than 300 degrees Celsius. And therefore, there are fewer scattering center. An electron in the wide bandgap semiconductor can achieve high peak velocity. It has high breakdown voltage also due to the large electric field required to generate carriers through impact mechanism. So it's good for high power application. And of course, it's not easy to grow gallium nitride and aluminum gallium nitride. High cost, reliability issue. Silicon carbide also used for high power, high temperature application, and it's a good heat sink. And the disadvantage, of course, is also the reliability issue and its high cost. Next is the important semiconductors for light sources. For example, gallium arsenide and aluminum gallium arsenide have been used for decades in laser and LED technology. And especially the most important application in the recent year is in the laser sources and waveguide technology for data network, laser diode, photo detector technology for advanced 3D imaging. So aluminum gallium arsenide, the X, the 1 minus X, refers to the fraction of gallium in the gallium arsenide that are replaced by the aluminum. So sometimes the X is known as a composition or mole fraction. It ranges from 0 to 1. So if it's 0, then you have only gallium arsenide. If it's 1, we have only aluminum arsenide. So if its X is 0.3, means there are 30% of aluminum, and 1 minus X will be 0.7, which is 70% gallium. We'll discuss more of the semiconductor alloy in the later part of the course. Indium gallium arsenide phosphide quaternary alloy. It can grow lattice match to indium phosphide and is useful for communication application, especially in the 0.98 micron to 1.55 micron long haul communication. Gallium arsenide phosphide is good for light emitting diode with nitrogen doping. Remember, nitrogen is group 5, phosphorus or arsenic is also group 5. So it's not a shallow impurity, even though we call it a nitrogen doping. So the nitrogen will either replace the phosphorus or arsenic, and nitrogen introduce a trap level in the band gap. However, it helps in the green light emission. So, and especially for gallium arsenide phosphide, if you replace some of the phosphorus with nitrogen, it can give you in the red light emission. Gallium phosphide, the phosphorus replaced by nitrogen, it can emit light in the green wavelength. Okay, other composition can give rise to orange or even yellow color. Now, quaternary aluminum gallium indium phosphide, especially they use in the quantum well and the application especially in the traffic light where they form the red, yellow and orange LED. Indium gallium nitride, large band gap material. Because gallium nitride is a large band gap material, indium nitride is a smaller band gap material. So the indium gallium nitride actually is important for the light or for the blue light emission. Other materials that can be used for the blue light emission are zinc sulfide, zinc selenide, and silicon carbide. But there are issues, okay, in their doping structure as compared to indium gallium nitride. So the current technology for blue light emission is basically using indium gallium nitride. And indium gallium nitride also been used for laser diode. Important semiconductors for detectors: indium gallium arsenide ternary alloy, excellent for long-haul communication in the 1.55 micron, and you can find a substrate indium phosphide that can be lattice matched. For even longer wavelength of 2 micron, okay, we can use aluminum gallium antimonide. But it's not easy to grow because there are not many available substrate that you can grow aluminum gallium antimonide with a lattice matching. So one of them is gallium antimonide, but it's very expensive wafer to produce. Indium gallium arsenide phosphide quaternary compared to indium gallium arsenide ternary, basically it gives you a wider range of the wavelength, so it's again suitable for telecommunication 1.55 micron and 1.3 micron. Mercury cadmium telluride, okay, is an excellent material for long wavelength application in night vision, or you can even use for your night vision goggle, and also thermal imaging. The wavelength is 2 to 5 micron. Standard silicon and germanium, as you have studied in your undergraduate day, silicon have a bandgap 1.1 micron, germanium 1.85 micron. They are good for avalanche photo detectors. Gallium nitride, okay, the wavelength or the bandgap, okay, is in the 0.36 micron or 3.4 eV, used for UV detector. So the detection of UV radiation using gallium nitride can have a wide range of applications such as chemical, environmental, and biological analysis or monitoring. A high performance photo detectors, okay, you need to satisfy high sensitivity, high signals to noise ratio, high spectral selectivity, high speed, and high stability. So this diagram basically summarizes the semiconductor photo detectors and their application. So UV semiconductors, for example, gallium nitride or tin oxide, has a wavelength in the ultraviolet or UV region, can be used for pollution detection. Visible for imaging, there are many semiconductors have wavelength in the visible region, can be used for LED laser and imaging. Near infrared for bioimaging, for example, semiconductor such as lead sulfide, which is 4-6 semiconductors, grow in the form of quantum dot or nanocrystal, have wavelength in the near infrared that can be used for bioimaging. Telecommunication, short wavelength infrared, such as indium gallium arsenide, can be used in the optical fiber to transmit signals, internet communication, and cable television signal. Mid wavelength infrared for chemical analysis, and then you have also long wavelength infrared for thermal imaging. For example, mercury telluride can be used for thermal imaging. And then medical imaging, you need devices, okay, that make use of gallium arsenide for terahertz application. So this is a range of wavelength for visible, near infrared, short wavelength infrared, mid wavelength infrared, long wavelength infrared, far infrareds, and terahertz range. So this is another summary, okay, for all the wavelength that is needed in the semiconductors. Now, this slide basically shows you a spectral attenuation of a silica optical fiber. So it's attenuation as a function of wavelength. So the red curve is basically the spectral attenuation of a silicon optical fiber. And it's a sum, okay, from the Rayleigh scattering, the UV absorption tail, okay, and also the absorption from the OH group. Now, silica optical fiber is used for the optical communication. The 1.3 and 1.55 micron, the attenuation, okay, is basically it's the smallest, and it has been used for telecommunication. And is chosen mainly due to the absorption characteristic of the glass material used in the fibers. For short wavelength, okay, in the short wavelength region, the blue curve, which is the Rayleigh scattering, become important, especially in the UV wavelength. And towards in the UV wavelength, you also have a ultraviolet absorption tail. Due to the electronic absorption, they start to kick in. Now, Rayleigh scattering is basically scattering of light off the molecules of the air. So for example, Rayleigh scattering of the sunlight in the Earth's atmosphere causes the diffusion of the sky radiation. Now, at the 1.4 micron, okay, you see the green curve. These are strong absorption OH group, the green curve. Okay. The water molecules in the atmosphere give rise to absorption of electromagnetic radiation. Now, at the long wavelength, if you look at the purple curve, besides in the UV absorption tail, which is a short wavelength, at the long wavelength, you can see that it starts to increase. This is the infrared absorption tail. So basically, you leave only two windows, 1.3 and 1.55 micron, which have low absorption, and that can be used for optical communication. So that has ended the chapter 1. And this is a list of appendix for the fundamental constant, which we will provide you in the examination. That's end chapter 1.